Very much for the introduction. Mic's on, you can hear me? All good stuff. Thank you so much to the organisers for inviting me to come and speak to you all today. It's always lovely to be able to come and talk to such an electron microscopy focused audience. And when I was thinking about what I wanted to talk about today, I wanted to really, I guess, reflect on the journey that we've had at Leeds. So we had our 2 Titan Krios installed back in 2016 now. And looking back at how things have changed, an awful lot has changed, and actually specifically in the last 6 months we've had a large number of hardware and some software tools come online, which I think are really changing the face of single particle data acquisition. So thanks to Karen yesterday for giving a lovely talk and introducing some of these things already to you. I think we're all aware that new hardware is coming online in terms of new detectors, particularly the Falcon 4, Falcon 4i and Selectris. There's been the introduction of fringe-free imaging. So for those of you who maybe haven't had time on a microscope, this essentially allows you to use a smaller probe size, smaller illuminated area and squeeze in more shots per hole. More shots per hole, the fewer stage moves you have to do, so that essentially the more images you get, the faster it goes. Aberration-free image shift collection, or AFIS or AFIS, depending on your tomato pronunciation, again allows us to collect data more quickly. So set of calibrations where in a single stage move we can take images across multiple surrounding holes, and again this really speeds up our single particle data collection. So we've been bringing all of these new tools online in terms of new and faster detectors, the optical changes with the fringe-free imaging and AFIS data acquisition. So what we wanted to do is really step back and say, well, how is this impacting your average cryo-electron microscopy experiment? So all of the work that I'm just about to present has been done by the electron microscopy team at Leeds, and I'm incredibly fortunate to work with this very talented colleagues. So we have Yehuda, Josh and Louis, who have done literally all of the legwork and hard work on the data I'm about to present. So what we did was took a protein sample, and I was very keen not to use apoferritin, because I think at this stage in my career, if I see another apoferritin structure, I might scream. So we chose something which is biologically a little bit more interesting, and also has a little bit more challenge associated with it. So it's not quite the brick that apoferritin is. It's not huge, but it's certainly not tiny. It comes in about 360 kilodaltons, and it does have C2 symmetry. And big thanks to Colin in Cardiff for letting us steal this protein. So Louis prepared a single grid using this protein, and those of you who've used Krios recently, you see in the software there are these automated tools to identify regions of similar ice thickness. So we basically identified regions of the grid where we thought that the grid squares were relatively homogeneous, and we collected a series of data sets. I should say we're going to write this all up for a publication, which is going to have a lot of different individual data sets in it. But in the interest of time, today I'm just going to talk about the data sets where we've used AFIS and fringe-free imaging. So we've tried to increase the throughput in terms of what the microscope can do. So we essentially, over a number of months actually, collected these data sets, and throughout the experiments we tried to keep everything as consistent between these data sets as possible in terms of pixel size, the recommended dose on the detector in a particular mode, shots per hole, those kinds of things. So we collected multiple 4-hour data sets with all of these different detector configurations. And for those of you in the audience who've used the Falcon 3 and a Falcon 4, this is going to come as no surprise. Falcon 3 counting, we see about 4.5 times more data moving from Falcon 3 to Falcon 4 in this experiment. So the difference between those generations of detectors, pretty huge. Ironically, by the time you've got fringe-free and AFIS on there, the Falcon 3 linear actually does produce the most amount of data in terms of sheer micrographs, but I'll come back to later why you probably still don't, if you've got a preference, you still be wanting to go for the Falcon 4. So we collected those data sets, and then Josh mostly led on this processing. So processed all of these data sets through a consistent Reliant-based pipeline using Cryolo to pick the particles. And we got some nice structures out, and they all look as they should in terms of the structures. I should say that these are laughter filtered. Any questions, we can direct those towards Colin later. So So yeah, we've got structures. They all, none of them are junk. They all look as they should for the biological specimen. So what I wanted to do now was just show you the resolutions that pop out of that. So again, this is probably no surprise to anybody, but the data that we got from the Falcon 4, the nominal resolution from that reconstruction was better than the Falcon 3 in either mode. And I must admit, I was slightly surprised, although this has been also reflected in many different projects that we've had through the microscopes in Leeds. Collecting your single particle data on the selectors does seem to give you a consistent improvement over just using the Falcon 4 alone, which is interesting. And again, just as an indicator in terms of data quality, if we have a look at the automatically estimated B factors that come out when you do your post-processing in RelyOn, we see a really clear trend in that, which I think is giving us some indicator that we're seeing improved map quality. Of course, in these maps, there are different numbers of micrographs and different numbers of particles. So this trend that we're seeing could be simply particle number driven. So Josh went through and selected 10,000 random particles from each of these data sets. I should say they were random good particles out of the polishing step. And again, look to then reconstruct those. And again, we see the trend being borne out that the Falcon 4 is giving us an improved data quality. And again, the selector seems to give us an improvement. So what does this mean for our single particle data acquisitions? Well, then the main thing for me, which actually slightly blows my mind still, is that this is not apoferritin. This is a relatively annoying biological specimen. Don't get me wrong, it's not the worst thing in the world, but it's certainly not the easiest thing to work with. And if we have a look at the amount of time that it takes to get 10,000 good particles, on the Falcon 4, we're essentially looking at 16 minutes to get a 3.5 angstrom structure. So, and this is a project where, if I have a look at the last several years, probably we would have looked at a grid, done a sort of a manual screen on that, and yep, particle distribution looks good, we'll go and collect a 48-hour data set. And when you suddenly realize that actually probably collecting 48-hour data sets on almost every biological specimen, not all, there would always be some exceptions, it's probably too much data, and we probably don't need to be collecting that much. So in terms of conclusions, again, most of these are not very surprising. AFIS and fringe-free imaging make a real difference to the throughput on the microscopes and allow us basically to collect data faster. The Falcon 4 is much faster than the Falcon 3, but also seems to be giving us improved data quality. And again, we seem to be stacking then an improved data quality when we add the selectress on top, which is just really interesting to see. And I must say, I'm really enjoying the selectress experience at the moment. As of last week, we've had Falcon 4i bits sat in a box since February, but as of last week, they are now on the microscope, and we're very, very excited now to be going through and repeating this experiment with Falcon 4i data, just to see again what that does to throughput, what that does to time to a relatively decent reconstruction. So what does this mean? I think one of the reasons I find this so interesting is that as a facility, we're really resourced and set up to be training users to screen and then training users to set up a data collection for 24, 48 or 72 hours. And when we were on the Falcon 3 and K2, that was how we were running the facility. And we're looking at the kind of data that I've just presented now and saying, actually, that's probably not the most efficient way that we can be running our microscopes. So for people that work within facilities, as amazing and fantastic as they are, they need sleep. So we can't be in a position where, if we're looking at getting maximal stuff out of our instruments, how do we structure our operations in such a way that we're maximizing what happens on the microscope, but not making users or facility staff be working routinely out of hours? So we're doing a lot of thinking in the facility at the moment about how we approach that. And I think there are a number of tools which are either in development or kind of coming our way, which are going to make a difference. And yeah, multi-grid EPU is something that I'm very excited about, and I think will be great, because it means the idea is we'll set a data collection going in the afternoon, and we'll come back in the morning to
12 mini data sets, ideally, that have all been put through the wonderful image processing pipelines that Matt presented yesterday, and it will all be highly efficient structure determination solving machines. And finally, it's around training. So I think there's a question there around how we can empower users to be able to make the most out of their microscope time. And I think we probably need to make some changes there. Okay, so all of that kind of leads me on to the next section of the talk, which I've got to say is potentially the slight, I don't know if it's less optimistic, but I think this really illustrates to me that sample preparation in the majority of cases is really our major bottleneck and something that we need to do something about. So the next section of the talk, I'm going to talk about sample preparation, and this side of the project was really led out of Steve Munch's group, who's here and at the back, so you can heckle him later. And again, in terms of the work on the ground, the sample preparation team is David Klebel, who's an amazing PhD student who's just passed his Viva, in fact, and Yiheng and Izzo, who are two brilliant PhD students working with Steve and myself. And then there's Howard at the back, who did a lot of the development work with the time-resolved electron microscopy device I'm going to talk about in a minute. And we're very fortunate to be working with Michelle on the aspects of the project where we've been looking to have a look at what the chameleon can do. And I think there's really exciting things there. So, as most of you in the room are probably aware, and I did this quick survey a couple of years ago now in Leeds, pretty much every single project that comes through our doors from a cryo-EM perspective needs some kind of optimization, whether it's preferred orientation, your ice isn't the right thickness, you've got compositional heterogeneity, maybe the thing loves sticking to the carbon. You know, it's very, unless you've got a beautiful icosahedral virus, which Neil has a lovely habit of trying to bring some of those samples through, pretty much almost everything needs at least one round of iteration going through. The good news, or the bad news, is that there are a huge number of tools in the literature that have been reported to allow users to go in and make changes to hopefully alter their particle distribution on the grid and to help overcome some of these issues. I think it's really striking to me that as a field, we haven't necessarily been able to settle on very many universal solutions to these problems. And I think, you know, the problems that are highlighted here are caused in a large part by interactions at the air-water interface. So, essentially, I guess Steve and I are particularly interested in looking at the air-water interface and saying what is going on there, essentially what can we learn about that, and how it then impacts downstream structure determination. So for this side of the project, we've been using the time-resolved electron microscopy device, which has been developed between Steve's group and Howard White. And essentially what this does is it sprays, is that video playing? Can never tell because it's so fast. There we go. Essentially what it does, it sprays small droplets onto a grid and then plunges those into liquid ethane. So we can make grids on essentially on a millisecond time scale on this one. So not quite as fast as as laser melting, but still pretty fast. I guess summarising some of the work that's been done in previous years, I think there is a real consensus and an understanding now that even if you're making grids on these very short, you know, smaller number of millisecond timescales, it's been shown theoretically and also empirically now that for the majority of projects, your particles are sticking up at the air-water interface, you know, within a millisecond timescale. So you can't outrun the particles interacting with that interface. But what are they doing when they're there? Well, again, a paper all the way back into 2020 now, which is mildly terrifying. In a paper, we described a number of things that can happen, and one of them, which I'm sure again most of us are all very unfortunately familiar with this, the air-water interface can cause preferred orientations. And I think for me, the really interesting thing about that is that the preferred orientation is not necessarily linear. So some of them will get worse over time, some of them will actually get better. So I think, again, that just shows that not all biological specimens behaving in the same way. We've also been able to show that you will get regions of proteins which either dissociate, denature, or become disordered, again, in a time-dependent manner. And again, how long it takes varies according to the specific region of a protein that we're looking at. So we know that these air-water interface interactions are causing impacts which are essentially, I guess, harming our structure determination process. And I think that the ones I've just described are probably pretty well understood in this room now, which is great. But basically, we got thinking what other processes might be happening at the air-water interface that maybe we haven't fully considered yet. And I've just shown a couple of pictures of apophyrosin here, which was prepared within 50 milliseconds. And you get all sorts of weird aggregates forming and things like that. And I think we felt for a while now that there's probably some additional things happening within this thin film environment, which should probably have implications for our biological specimens. So in this next stage of the project, so as part of the work that I've just described, which was published back in 2020 now, David Clevel, so again a PhD student, spent an awful lot of time looking at HSPD1, which is this protein, and he ended up noticing that on this particular cysteine, which is surface exposed cysteine, on this protein, there was a weird additional density associated with this. And he noticed that in the region of this cysteine, there was a loop region, which he was essentially unable to resolve. And going back and looking at bacterial homologs, it was clear that in those structures, the loop was perfectly ordered. So we kind of thought this was a bit weird, didn't really know what this weird extra lumpy density was. So David then went back to the data set that he collected very quickly, that he'd frozen quickly. So this is on 14 milliseconds, and looked at this same region and found that there was no cysteine modification. There was no additional weird lump on that cysteine, and lo and behold, that region was perfectly ordered. So we started to hypothesize and say, well, is the modification on the cysteine responsible for then that downstream structuring change? And also, what is the lump on the cysteine? What's going on there? Well, we had a funny feeling it might be oxidation related. So went back and made a blotted grid with the addition of DTT, reducing agents in the buffer. And it was essentially able to see, again, you've got your cysteine, no weird density, loop nice and ordered. So whatever it is isn't related directly to the blotting process. We can use DTT and essentially protect against this happening. So in terms of then the next stages, we thought, well, this is all very weird and very interesting, but at the moment it's one cysteine on one protein. Potentially we've just got something weird going on with this particular system. So this is where Yihan came into the project and said, aha, well, let's go and see if we can look for this in other systems. So we looked at beta-galactosidase, and we were able to see, again, if you just make a normal blotted Vitrobot grid, you can see that this particular cysteine residue, again, has got a weird, lumpy additional residue, additional density associated with it. And once again, if you make grids quickly, so again on 18 millisecond timescale, we see no additional density. And finally, if you make a Vitrobot blotted grid, again, exactly the same as in the first example, but just with a bit of DTT added, then again, we see there is no additional density. So I think that gave us a good indication that what we were seeing was not a protein-specific phenomenon. And really interestingly, we were finding consistently that either making grids quickly or introducing a reducing agent was essentially protective. And the addition of the reducing agent, I think, gave us quite a lot of confidence that probably what we were looking at was oxidation within the thin film environment. And for those of you with beady eagle eyes, you'll see it's not quite as striking as it was in the previous example, but we are seeing some subtle structural changes. So, for example, the histidine rotamer that you can just see towards the south of that image is in a slightly different orientation. Actually, quite a different orientation. So we're seeing these impacts, and we're seeing either subtle or not so subtle structural changes occur as a result of these. So the next thing we wanted to look at was whether this is happening within the thin film environment, or whether we think this is happening at or in very close proximity to the air-water interface. So it's been well described in the field now that when you have a continuous support film, you'll get the particles absorbed onto that continuous film, and they'll be away from the air-water interface. I should point out that there are lots of forces that might exist at the support water interface as well, and I think that these are potentially less well understood even than the air-water interface. but they exist, but it at least gives us an ability to be able to essentially run a control. And again, we found that if we had a look at these grids which had been blotted, but where the particles were absorbed onto a continuous support film, once again, we see no weird additional density on our cysteine, and in this case, the histidine rotamer is back where it was previously in the fast grids, for example. So that gave us some confidence that this phenomena that we're seeing is likely to be modification that is occurring essentially at or in very close proximity to the air-water interface itself. So let's go back. So these structures that we were looking at, we're looking at residue by residue and quite subtle structural changes. But I think one of the interesting things to come out of this for me, and I'd be interested to hear if anyone else has done this, I've been getting some anecdotal evidence from users who come in to use the facility, probably over about 12, 14 months now, saying, oh, well, I had aggregated protein, so I stuck DCT in. Like, well, why did you add DCT in? Oh, well, because somebody told me it helped them, and I think I wanted to try something to make my particles less aggregated. And actually looking at the raw images that we're getting, obviously there are some differences in concentration here, but we can see really clearly when you add the addition of the 1 millimolar DTT, we're seeing a more monodispersed particle distribution. And I'm going to caveat this, and I'll caveat it again at the end. Sticking in 1 millimolar DTT is potentially quite risky and will have other implications in terms of your protein structure. So I'm not necessarily advocating this as a universal approach, but it's interesting to see it coming out in these particular images. So what do we think is going on here? And I'm going to just caveat the whole rest of this bit by saying I'm not a chemist, and if anyone has some ideas, I know Steve and I would really love to come and have a chat with you. But it has been reported in the literature that a very large electric field exists across the air-water interface itself, and that this might be of a magnitude sufficient to actually split water molecules and create hydroxyl radicals. So the current working hypothesis is what we're probably looking at is spontaneous oxidation in the thin film caused by these free radicals. So I think hopefully we've been able to show that we think there is this oxidation, or certainly chemical modification of these cysteines. We've got this weird density appearing. And really interestingly, we can see that reducing agents, so an addition of DCT, making grids at speed, or sequestering the particles onto a continuous support film are all strategies that appear to stop this from happening. So that's quite interesting because it means that we've got many options in terms of investigating this going forwards, which is always nice. Wanted to highlight that I've shown you some specific residues today. For example, beta-galactosidase, there are other cysteines which are surface exposed where we see this. There are also some cysteines where we don't see this. So there's obviously something going on there that makes some regions more susceptible to this than others. That's still something we're looking to understand in terms of the local chemical environment around those residues and looking at how that might influence essentially. The structural changes that we've seen and we've reported today are subtle. There are changes in rotamers, their loop regions becoming slightly less or becoming less ordered, and you're not able to resolve those. But if that's the region where your Fab is binding to, for example, then actually this might be really meaningful for your structure determination exercises. So I think we're still at the beginning of fully understanding the implications and looking for more examples of this happening. But I think it is interesting to see this chemistry within the air-water interface impacting the structures that we're solving. Another thing we're not very sure on, again, I'm not a chemist, it may be that we think theoretically there will be other residues, not just cysteines, that are potentially impacted by that. So it'd be interesting to go and see if we can investigate that. Again, I'm just going to come back to that. Adding a reducing agent, particularly DTT, may have other implications in terms of your structure determination. So if you're going to try it, try with caution, I would say. And then the final thing on this one is just a little bit of a plea. So there are, between the people in this audience and certainly the people online, there is a lot of knowledge about your specific protein structures. You're very intimately knowledgeable about your proteins. So Steve and I would absolutely love it if you could possibly go back if you think that you found an example of either a modification or some potential structural changes, it would be great for us to start to try and collate some wider examples of that, so we can start to essentially design some experiments to work out what's going on. So yeah, so if you have a funny looking cysteine, get in touch. Okay, so I've got almost no time left, so I'm going to do some extremely quick plugs. And the first one is just talking about training in electron microscopy. So Leeds, in conjunction with many other sites, including EBIC, are running a community-led training program in cryo-electron microscopy. We're shortly going to be launching new training courses, so keep your eye out on 3D-EM. And if there is a type of training which you really want to receive, I'd love to get an email from you and have a chat about that, because really this program is to support the community to get hands-on training in sample preparation and electron microscopy. So yeah, please do get in touch if you're interested. Next bit of a plug, and I think Kyle might have mentioned this. Big thank you to Tom and Angela from STFC, who are building us a electron microscopy community SharePoint site. And the vision around this is that it will be a one-stop shop and repository where any sites that are essentially interested or willing to do so will be able to contribute resources, SOPs, that kind of thing into a single repository, so that if you need to write a VitraBot guide, you don't have to start from the beginning. You can take one that's written by Leeds and one that's written by EBIC, and then you can take the bits that you like from both of them and hopefully save yourself a lot of time. So watch out for announcements on that soon. And then final obligatory plugs. So at the University of Leeds, we do offer access to our instruments free at the point of access through Instruct and iNext Discovery. I'd love to give you some more details on that if you're interested. So come and talk to me or anybody else in the electron microscopy team. You can also just come to us direct if you want to essentially pay for access. And the final plug was just for the this Faraday conference, which is happening in Sheffield in July. There's a really interesting program lined up, and the organisers, as a result of this conference, have extended the poster deadline, which is now on the 23rd of May. So I think there's going to be an awful lot of interesting cryo-EM methods-based discussion leading on from a lot of the topics that have been discussed here today. So please do go check that out, and hopefully might see you there. Okay, great. So that's all I've got to say. I just really wanted to acknowledge both the direct people who are involved in the work, who I've mentioned as we've gone along, particularly the fantastic electron microscopy team that we have at Leeds. And I haven't been able to talk about the work of Tom, who is bottom right, who's our new correlative imaging scientist. We've got loads of exciting clem work going on at the moment. And I also wanted just to acknowledge some of the recent team and team alumnus who essentially directly run the instruments. We're extremely fortunate at Leeds to have a huge and supportive and diverse community of electron microscopy users. Ahead of this talk, I just ran a quick report, and in the last year, bearing in mind we were a bit hit by training and things like that, we had 88 separate internal users come and collect data on our Titan Krios microscopes. And ultimately, everything that we do as a facility is designed to support those people who are coming in and using the instruments. And it's just amazing for me to see the community that has grown up and the diversity and complexity of projects that they're looking to develop. So I just wanted to acknowledge the whole cryo-EM community at Leeds for making it such a wonderful place to work. And with that, I'm going to shut up and invite any questions.